Good morning, everyone. Welcome to the session, Artificial Intelligence for the GEO work programs. Actually, how to accelerate artificial intelligence for Earth intelligence. So we have a exciting panel today who will present diverse topics. So today, we'll start with audience survey. We want to know your background and your involvement in machine learning and also artificial intelligence, GEO work program, GEO activities. So first we start with a survey, then I will provide some opening remarks. Then we have panelist presentations. They showcase exciting application areas using AI. Then we'll have panelist discussions. We have no Q&A right after each talk, but you can save your questions to the panel discussions. After that, we have another audience engagement sessions with the Metameter, and then panel also contribute to answer some of your inputs. And in the end, we will stop with closing remarks, then also actions for the future. So first, I would like to introduce our great panel. So we have four speakers from Professor Bingfang Wu from Chinese Academy of Sciences, Yu Zhao from KTH Royal Institute of Technology in Stockholm, Sweden. Then we have Professor Torsten Jelinek from Taihe Institute. And we also have Lisa Marie Robello from Digital Earth Africa. So before the panel, I would like to briefly introduce the objectives of this session. We would like to explore the intersection between artificial intelligence and Earth observation to support sustainable development and environmental stewardship, and also contribute to GEO's post-2025 agenda, Earth Intelligence for All. And we would like to highlight AI techniques such as image classification, change detection, time series analysis, and also predictive models, how that can be used for EO data. And we would like to showcase real-world applications, including resilient agriculture, urbanization, wildfire detection monitoring, disaster management, among others. Finally, we will discuss opportunities and challenges in AI-EO integration, data quality, scalability, ethics, and interdisciplinary collaboration. So before that, we will start audience survey. So please use the QR code on your phone, and we would like to gather your input. Yeah, so it's free text, your input. You just answer the question with your own words. So let's see. Okay, the responses. Researcher, partner, first-time participants, leader of GWP. So let's see. So I have a variety of participants. Great. Looks like we have quite a few first-time participants from leaders, member countries, researchers, regional GEO coordinator. Yeah, so there are diversity of participants here, great. Yeah, nice to see so many first-time participants. It's the biggest group. Okay, next one. What is your application area that you use in Earth observation, or you use Earth observation? Great, AI governance, GIS. Let's see, do we have more? Climate change, adaptation, urban monitoring, disaster management, agriculture, human-centered design. Yeah, a lot of variety of application areas. Great. Biodiversity conservation, health. There are so many different application areas. Wonderful. So then we go to the next. What are the traditional machine learning methods do you use? All right, let's see. SVM, convolutional neural network, decision tree, SVM, CNN, yeah, that's convolutional neural network, random forest, SVM, decision tree, Google Earth, decision tree, LLM, SVM. So it's quite a few that are, overlapping SVM, decision trees, convolutional neural network, random forest. So those are seems to be common elements. Yeah, great. Have you used AI deep learning in your EO applications? So we here just yes and no. We want to see how many in the room have been using AI as a tool or developing AI-based technologies. So let's see. Well, we have majority yes, that's good. That's great. Nice to see. All right, let's see. We have more than 20 people here, so please have your input. Yeah, fantastic. Yeah, definitely majority are yes. All right, so here we established definitely majority of people who are actually using AI and very familiar with AI. So that's really fantastic. This is in line with the survey result from GEO that I will share with you in a little bit. So I would like to briefly talk about Earth observation, big data, how AI can accelerate we derive insights using, deep learning models and deep learning-based approaches. You all know with space agencies, European Space Agency, NASA, Chinese EO community, you heard about Professor Durnley talk about so many satellites are in orbit, and then private companies are launching satellite. We have many Earth orbiting satellites helping us to monitor our changing planet. And there are obvious opportunities. The opportunities are we have open access to majority of the data, but commercial entities also sometimes open data for research. We have multimodal EO data. We have multispectral, hyperspectral, radar, LiDAR data. We also have multi-resolution, multi-scale data sets from local, 30 centimeter resolution to kilometer resolution. We also have long time series of data. And in terms of AI for EO, we have advanced deep learning algorithms, models, automatic image processing, change detection, time series processing methodologies. We have multimodal data fusion that can accelerate applications in many different areas that you will hear about today. And what are the challenges we're facing? Deep learning models are usually developed by computer vision people that they use small natural images rather than the large satellite images and also long time series and more complex. We also have limited high quality training labels and maybe limited reproducibility and transferability. So these are challenges we're facing, and I'm not even mentioning maybe AI governance and ethics as well, but we will touch upon that today in the panel discussion. So I will quickly show a very quick example of one of my projects funded by GL and the Google Cloud credit program. As you all know, we're experiencing rapid urbanization with accelerating climate change. There are a lot of different environmental and health impacts of urbanization. And using AI and Earth observation big data, we have developed innovative methods and approaches to map urban areas more reliably. And we deployed this in many cities around the world and achieve a good accuracy from Beijing to Addis and to Stockholm, using only training labels from building footprint from North America. And we have also been working with urban change, monitoring urbanization on a continuous scale and continuously using deep learning models. So here are just some examples. We have deployed that in also 60 different cities, use SpaceNet 7 publicly available data set. And now we're going into, so the AI applications are really promising. How can we use artificial intelligence to accelerate Earth intelligence? So in the post-2025 GL agenda, including integrate Earth observation models and innovative new technologies. So AI is clearly mentioned in this post-2025 agenda as an important contributing elements. And so because of, after the GL symposium last year, we, together with GL Secretariat, and we made a survey to all GL programs and cloud credit programs. So we got quite a lot of responses, and you can actually see at least half are using AI in their work, either moderately or use at the advanced level. So that's very good. But the audience here is actually better. So I think we have over 70%. And also how are AI currently used within the activities? So image classification, predicting models, change detection, and automatic feature extraction are, among many are highly ranked being used. And what are the challenges or barriers have you encountered in implementing AI in EO? So here, people said data quality and availability is one concern. And there are two different kinds of data quality availability, lack of labels, annotation, and the other is limited and inconsistent data. So that's two elements in terms of data. Computational resources is also highlighted, AI model transferability, lack of expertise, cost and funding. So these are the concerns people have. And then we also look at what challenges and barriers have, okay, but this is the one. Future perspective. So what do you see AI can be used in GL, or what can GL support? So many said the working group of AI for EO or special working group. facility access to commercial satellite data, cloud credit programs that sort of respond to lack of computation resources, data, webinar, and workshop for special training opportunities, meetups, collaboration, sharing data, best practices, promote user open source, reproducible, reusable tools for you using AI, publications of workflow that's related to sharing, more open sharing and sharing high quality sample data, workshops and practical demonstrations. So this is really exciting, encouraging, and I hope the community, many of you using AI in your work can come and share this and together with us to build a community AI for EO. So with that, I would like to introduce our first speaker, Professor Bingfang Wu from the Chinese Academy of Sciences, Aerospace Information Research Institute. So Professor Wu, the floor is yours.
Thank you for your introductions. It's my pleasure to be here to share my what is we are thinking about how AI and big Earth data can be used for resilient agricultural practices. Yeah, we all know the UN Sustainable Development Goals, particularly for the goals 2, is zero hungers, and it will be good to develop a sustainable food production and resilient agricultural practices, which can support to ensure the zero hungers. So in here, the resilient agricultural practices has been mentioned to be here in order to increase productivity and the protections that help maintaining ecosystems level strength capacity for the adaptation to climate change and also the purposely improved land and soil quality. It's not good. I cannot see here. I have to there. But in this case, the data on the recent agricultural practices, there's a severe data scarcity. Present data challenges prevent the up-to-date and the comprehension of the refined understanding of SDG2. I think particularly for the recent agricultural practice, we are lack of data. It's not available on that ones. And therefore, to bring this data gap is one of our key tasks. We can use AI and big Earth data to support us on other ones. But however, the cost of collecting this data is very high. And also this another thing is to collect this involve multiple sectors and industries. But normally the list data are typically collected and analyzed independently, so leading to the fragmented data management and decentralized responsibility. And also the inadequate data exchange and sharing between the departments, even sometimes a conflict between the different set of data sets. So we need new models, new methodology to develop for the data acquisitions for the resilient agricultural practices. Now, of course, as mentioned also by Professor Bang, we do have a lot of data sources from different sensors and UV or that one. Uh, and also the big data and the AI technology can help us on that ones. And currently the data are, in fact, are no longer the constraints on the agricultural applications because especially there are so many data available from the internet. So the focus have been shifted to from the retrieve from the data to the retrieve and analyze those data for derived informations more economically and effectively, particularly for the resilient agricultural practices. And so next one, I will show data product for the resilient agricultures. Oh, sorry. I'm missing some, I think, slides. Sorry. Okay. This is not my version. I don't know why. Lose some. We are using AI and also the big Earth data to generate some of product relevant to the resilient agricultural practice. For example, the global production data to integrate to grid this data in data set at the 10-kilometer resolutions to let shows the land productiveness, grid land productiveness, and also this data can be used to assess the food security and also evaluate the climate impact on the land productions. And the first and the second one, we are developing using the AI, particularly, and with support of Earth observing data to derive the global agricultural field sizes over the globally, and this can help us to identify where the agriculture is intensive, where the agriculture schedule is very small field size. So you can see here, only 33% of the world's global land is cultivated with large scale, and particularly is in the North America, Europe, and the South Americans. But for the rest of the world, 60% of global land still a very complex global structure and very small field sizes. And you can see the red color in the left in the global field size is small, particularly in China, India, and Africans. But for the other three areas, it's a very large field sizes. And there is also using big also that we can derive the global type estimations, which is particularly for those small field sizes. Is hardly to directly to obtaining the global type airs with the current data. So we are developing procedures from global land to arable land to farming land and to global tax to integrate of big Earth data and artificial AI technology and also field workers together. For example, if you are it's easily to use big Earth data to obtaining global land, arable land, and farming land. But it's hardly to obtain the global type airs because small airs, small polar size. So in this case, the field workers, field workers with AI can be integrated into together to be effectively to obtain the global type airs. And also we are using AI and also because data to derive the agricultural wind black forest. This because over the world there are several areas like North China, okay, and also in the United States there are a lot of wind black forest. So we are employing the AI technology to obtaining this wind plague forest for this, and also particularly for the North China, we are quantifying all this. Totally, the wind plague forest occupied about 5.5% of global land. And also, both can be linked together, global parcels and wind plague together can be linked together to assess how the global land, global agricultural ecosystem works on these ones. And another thing is a terracing. Terracing is important also, not only for protecting soil erosion, but also can improve the land productiveness. So AI can be also used to map the terrace everywhere in the world. And this is a global terrace mappings we are used on other ones. And okay, together, all these informations, not all it can be integrated together to assess the agro-ecosystem atlas, because GEO now is launching, initiate the global ecosystem atlas. In response to this call, we are now launching the agro-ecosystem atlas study programs. We are choose China, Thailand, and the Zambezi Basin, River Basin in the South Africa as a two parallel sites to work to study how we can develop the agro-ecosystem atlases. And some of brochure flyers is distributed in the floor. You are welcome to join us on these study programs. Thank you.
Thank you very much, Professor Wu, for the excellent examples of AI applications in agriculture. So our speaker, next speaker is Mr. Yu Zhao. He will tell us about how he uses Earth observation and AI for wildfire detection and monitoring. Yu is from KTH, Royal Institute of Technology in Stockholm, Sweden. So Yu, the floor is yours.
Hello, everyone. It's very honored to be on the stage. And I'm Yu Zhao from KTH Royal Institute of Technology. And so I'm supervised by Yifang Ban, who is the head of division of informatics. I'm also very happy to be back to Hangzhou, where I spent 4 years in Zhejiang University. First, let's go through some of the outlines of my presentation. The first part will be the background of current wildfire status and what's the current methodology for wildfire detection. And for the rest of the presentation, there will be majorly 3 sections. For the second section and third section will be our current progress in using the time series deep learning and the various image time series for active fire detection and burn area mapping. And about the last part, I would like to share our current progress using the SAR sensors with different polarization and different wavelengths for burn area mapping. First, about the background of current status. Wildfire has grown in its both intensity and frequency in recent years. In 2023 alone, in Canada, there are more than 18 million hectares of burn areas in total, which caused severe damage to the global forest and caused a loss of carbon emissions. And similarly, in 2024, there was a huge wildfire event in Greece, which burned out the whole town. And in the end, it becomes one of the worst wildfire on the European soil. Then about current Earth observation for active fire detection, since active fire detection requires more about the frequency of the detection, then the temporal resolution becomes extremely essential for this kind of task. As for under this requirement for temporal resolution, we have basically two choices. One type of satellite is geostationary satellite, which are, for example, GOSAR, Meteosat from Europe and FY4 from China. It provides every 15 minutes of spatial resolution, and usually the spatial resolution is 2,000 meters to 3,000 meters. As for the other type of satellite, it's mostly the coarse resolution polar orbiting satellite like MODIS and VIRS. It offers twice daily temporal resolution and 250 to 1,000 meter spatial resolution. And on the right-hand side, there are two examples for this kind of satellite. On the left-hand side, that's animation from the GOSAR images. It has the color composition of mid-infrared band and two thermal infrared band. As shown in the animation, the wildfire can be visualized in the bright spot, in the red spot clearly, but the spatial resolution is pretty low. On the right-hand side, that's a visualization of mid-infrared band using the SOMI NPP VIRS images. And for this kind of satellite, it has better spatial resolution, but the temporal resolution is lower. And for the rest of our work, we were using the satellite images on the right and using the time series deep learning model to help us to detect active fire and burn area. When using VIRS for active fire detection, we used all 5 imagery bands from VIRS sensor. They all provide 375 meter spatial resolution. And among all these bands, the band I4 is the most effective one. And on the right-hand side, that's a plot we made when we're sampling the active fire regions and for regions unaffected by the wildfire. Assume there is a wildfire event on September 8th, then there's a sharp increase with the band value I4 during that day. But for the non-unburned areas, the value of band I4 remains stable. To capture these temporal anomalies, we propose using the time series deep learning model to fix this. Then this is our main methodology. I will quickly go through what we do with this methodology. So basically, we feeding the pixel time series to a transformer encoder. And then we are classifying each pixel into fire and non-fire pixels. And then we're putting back those pixels back into its original location to generate the final active fire map. One thing to be noticed is that inside the transformer encoder originally didn't have the auto-regressive mask. We enabled the auto-regressive mask to enforcing the temporal dependencies from the back, from the past information. Which we will also use that in the later stage. So in the end, some of the qualitative result. So we are comparing the result when using the UNet, classical UNet, and also the active fire product from NASA. And then the third row is our product. When comparing with the NASA active fire product, especially during day 9 and day 10, there are a lot false negative. Major active fire points are missing from NASA, but we managed to detect them in our product. But when compared with the UNet result, UNet has a bit false positive detections around the active fire points, which leads to lower F1 score in the end. And this is a wildfire event in Australia in 2019. This also highlights the possibility to make our deep learning model for operational use. So we tested further in South America, Africa, and Canada to test more fire regions. Compared with NASA VIRS active fire products, which is on the bottom, it has way more false positive detections, which cause extra effort for the firefighters if there are any. Especially if you're looking at the third column near the lake, the base image is from Sentinel-2. There isn't any active fire pixels, but we managed to detect them. So the other part is burn area mapping using the same satellite. Similarly, for this kind of satellite, we have two different sections, two different parts. One part is using the mid-resolution satellite. which has 10 to 60 meters spatial resolution, and every field is temporal resolution. And we can also use the various time series for this. And for this kind of method, we're using the 3D transformer, which directly feeding the image time series. And also, we enforcing the temporal dependencies by introducing the autoregressive mask inside the swing transformer block. In the end, we're generating those burn area masks every day for those two different wildfires. We generate also the animations for them. When comparing the detections, we are having less false positive detection and false negative detection both for this wildfire event. And the other wildfire events inside the wildfire, we can see our detections is much better than the baseline virus actifier product, which is accumulated from the beginning. Then some of the methodology we use in detecting burn area using dot polarization, C-band, L-band data, and for the compact pole. So for this kind of methodology, we use the similar architecture, basically using the SENtinel2 as a polygon to filter the log ratio, binderize the log ratio image from the GRD product. The GRD log ratio is the difference image between the post-fire and the pre-fire image. And then for using the compact pole, we have more options with the useful features. We generate the MT decomposition image and also the compact polarization radar vegetation image to help with the detection. Then for the first work, we try to distinguish the L-band and C-band in the effectiveness in burn area mapping under different burn severities. Then we can see that using the C-band, we misdetect the false negative, we misdetect the burn area at the bottom and also on the top right corner, which has a low burn severity. Also, the quantitative result, which also agrees that the Pulsar-2 gives much better result in detecting the low and medium burn severities. And then the last part of the work is about using the compact pole with compact pole decomposition and the radar vegetation index. The second column is a log ratio image, and the third column is compact pole decomposition image, and the last one is a radar vegetation index image. And as we can see from the visualization, the third row and the third column and fourth column can be a good complementary to the log ratio images we show. And we are managed to detecting most of the burn areas in the first column. Also, the quantitative results shown that by using all data source, we are managed to detecting better than using only the log ratio images. But we also try to only using the radar vegetation index and the compact pole decomposition, which has way worse detection result. That also highlights these two data sources can only be used as a complementary data source. That's all from me. Thank you.
Thank you, Yu, for sharing your work regarding how AI can be used to leverage multi-sensor, multi-resolution EO data. So our next speaker is Professor Torsten Jelinek from Taihe Institute. So Torsten, the floor is yours. Please welcome.
Bring my mobile that I can read it. It's wonderful to be here. Oops. Eh? Oh, there's some missing. Okay. I will be covering actually kind of three parts. It's a little bit quickly the evolution of AI technology that where we're heading to. Then introduce or talk about multi-agent systems and how it might impact. And then the AI governance gap or the usage gap that we face, despite all the great technology, who's using it actually on a subnational level, etc., to fight or to resolve the SDGs. So basically, we moved into like 3 or 4 stages from the classical causal AI, which existed since many, many years. Then we had a breakthrough with predictive, and we had a lot of insights now in the previous talks. The breakthrough was here, certainly 2012, around Geoffrey Hinton in neural networks. Then with the introduction of the transformer, which is already applied successfully, as we could just see. The breakthrough was here 2017 with this seminar paper published. And that 2022, we have the multimodal systems, and now we're heading towards generative, or we are full in the generative AI situation. What is the next step? And this is a little bit of a betting. Do we need more compute or better architecture? So we are already heading a post-transformer, non-transformer architecture, or do we need more compute, more data, artificially generated data? I think currently the betting is on both, and certainly more compute, as we can see happening here. And I will concentrate on the generative part. So from the previous talks, we have seen that at any stage of the process of the Earth observation process, from acquisition, processing, analysis, and the usage, you're using it. Maybe most in the probably processing and analysis phase. AI has been used. But when you now look at the use of generative AI, maybe you could see it in maturity steps, how Gen AI could be used or is used already. First, you have a kind of a step-by-step manual prompting. You have a real-time data and memory augmentation systems. Then you come into basic agentic systems using agents, or you have multi-agent systems. This is actually what Gen AI is enabling. On the bottom one, the 4, I think here you saw, just a couple of weeks ago, I attended several conferences. One was in Las Vegas, a big AI conference, and it was only about multi-agent systems. So that was the emphasis. There was so much enthusiasm about that, not talking about maybe the risks at that time, but what is already possible in that you set up your agents, etc. So briefly, what is that agent, and how can we, what is an anatomy or high-level structure, is that the agent basically has a goal which is defined, predefined, or it defines itself the goal, has a plan, it coordinates, it acts, it can sense, obviously, with the world, and very importantly, it interacts with other agents. And so it kind of needs a collective memory to understand what it did, what it has to do, and there are different kinds of architectures you can build. So you can have a hierarchical architecture, or you can have a flat architecture. When you think of when I go back, when you think of the Earth observation process, remote sensing process, I think this would be a hierarchical structure. So you have this agent overall. Oh, I have a slide on that. Yeah, I go to here. You have an agent overall, which kind of coordinates all sub-processes. On the sub-processes, basically, you would have maybe a flat structure, because in certain, you don't know what those agents will encounter in each process. So the agents will organize themselves, communicate themselves, and the result will be then given back to the basically a kind of a master agent, and then pass on to the next phase. So I think the scenario you see here, it's pretty long term, but I would not say too long term. We are talking here maybe 5 years, 10 years, I would say. I think we were talking about 5 years, where you can parts of this process fully automate and have it run autonomously, starting with the acquisition of the data, planning the mission, executing the mission, calibrating the sensor of a satellite surveyor. Actually, the agents can do that. There's no human interference anymore. I think that's the scenario we, I think, should look at, be very ambitious. I think we were asked today to be very ambitious and to question what we're doing today, and see actually which use cases would be feasible to implement such a multi-agentic structure. Let me go quickly back. What is that? What are the features of this multi-agentic structure? It's autonomy, collaboration, real-time, adaptability, communication, reasoning, planning, shared memory, etc. Of course, you see some of engineering bottlenecks, and the core engineering bottlenecks is the reasoning. This is a key problem still in large language models and transformer technology. But I think with the next releases, we're seeing the reasoning will be also, I think, resolved. Currently, reasoning is also more handled as a tool, so that an agent, so when you have mathematical issues to solve, you use a different symbolic environment, and the result will become then back to the agent. So it's not that the LLM will do that yet, but it will use a tool to do that. But I think in the future, you will have what you see here, you will have the yellow box there, LLM, you have kind of a native, how do you say, native reasoning capabilities in the system. Let me go to the problem, as we all know, is a usage problem. You have all, and you saw this great work from the previous speaker. So you need very experienced scholars, almost an elite approach to do all that work. And that's a big bottleneck, because in the end, where the SDGs are implemented, for example, happens on the subnational level, happens on municipal level. Offices of mayors, they have to do urban resilient planning, etc. And there's no way they can handle those technologies. So you have to make it very easable. So it's a big governance gap we are facing here. About all those great technologies, so it's a lack of awareness, institutional barriers, uneven distribution, and not to forget the unequal access to those technologies on a global level, as the asymmetries we're facing here, and to close that science and data gap. I think that's also very important. I think this is a big governance task on the one hand. On the other hand, the progress with agentic AI could actually also help to bridge that. So having said that, I would not just rely on the technology. It needs a political will and active governance to accomplish that. We did some studies, and this is in Germany, where we spoke with local municipal levels, how they use it and what are the priorities. And this just reiterates what I just said. Thank you very much.
Thank you very much, Torsten, for showcasing the very exciting multi-agent systems and the capability that, and also challenges ahead. We will save the questions for during the panel discussion. So I would like to welcome our last speaker, Lisa Maria Ribello. She's from Digital Earth Africa. She will tell us about Digital Earth Africa, enabling advanced analytics for Earth intelligence. So please, the stage is yours.
So I'm going to take a short 10 minutes or less to just look at how we're enabling the use of machine learning through Digital Earth Africa, and look at some of the trends we're seeing, recent developments around interactive user experiences and the use of Gen AI. So given that Earth observation data are large, multidimensional, with temporal, spatial, and spectral reflectance dimensions, applying ML and AI comes with unique challenges. And this really is what we try to address through the infrastructure of Digital Earth Africa. So Digital Earth Africa implements the Open Data Cube technology, which is a package designed to support management and analytics around Earth observation data, as well as other data sets. So Digital Earth Africa is currently the largest global implementation of the Open Data Cube, with over 5 petabytes of data hosted in Cape Town. There are two key aspects of our infrastructure and our model that really support the use of machine learning. One is that we use analysis-ready data. So CEOS ARD are satellite data which are processed to a minimum set of requirements and organized into a form that allow immediate analysis. This also then supports and encourages interoperability through time and with other data sets, which really are key for developing complex analytics. So by enhancing computational efficiency and bringing together the Open Data Cube technology and the analysis-ready data sets, it enables us to overcome some of the limitations that we see with traditional data processing methodologies. And really, what this enables us to do as a program is to build technology pipelines that enable near real-time, large-scale, and rapid processing and analysis, and converting those into actionable insights. So what we do at Digital Earth Africa, we take the full Landsat Sentinel data archives for the entire African continent, and we process these into a suite of products. We make the data pipelines available in analysis-ready format, but we also process them into continental scale services. And it's a combination of these technologies that enable us to do that. So I'm going to look briefly at a couple of those and then some third-party applications. So our continental services and products, these are operational, so they're updated on a regular basis. They are all co-created, they're defined, they're demand-driven, so we only produce a service when a user comes to us and requests support in producing it. What I have as an example on the screen here is our suite of geomedians. These condense satellite imagery, so dense time series, over a period of time. So we have annual geomedians, we have 6 monthly geomedians, and we have 3 monthly geomedians. So for example, the annual geomedians take the entire annual archive of Sentinel-2 and process those into a high quality single image, which is then used as machine learning ready input. We also have a cropland extent product and a crop type map workflow. These are trained on the geomedians. So the geomedians are key inputs for further analytical workflows. We work with users to define specialist workflows, such as the crop type workflow. We also have a national wetland mapping workflow for wetland inventories. And these walk users through a series of steps, from data integration to machine learning algorithms to outputs, how to integrate training data, how to clean it, how to process it, how to select the models, how to use a multi-agent approach where necessary. But we also recognize the importance of building user capacity in understanding and stepping away from black box approaches. So the third part of what we do is supporting analytics through a suite of Jupyter notebooks. We currently have 150 open source Jupyter notebooks on the platform, freely available for all our users with the compute to support implementation of these. These cover various thematic areas, from agricultural analytics, water bodies monitoring, urban extent mapping, marine floating debris. As I said, there are 150 of them. These are all analyses which have initially been defined by the users, which then go through a series of specifications through our team, and then are made available to all other users. And this is really where the strength of the platform is seen, because of the scalable workflows. When they're applied in one location, a user in another location on the continent can take them and apply them using the same models or changing the models as needed. So there are some strengths to this approach. We produce the training models to support understanding of machine learning approaches. various models moving away, like decision trees, random forest we introduced before we move into the more black box approaches. We introduce concepts such as accuracy assessment, input parameter importance, clearly introduced and explained for ranging from entry point users to more complex capabilities. The future directions that we see from our users who come to the platform and the feedback we're getting is more and more around scaling. Once prototyping, users want to scale to larger areas. And this is an area we're looking at how we integrate further skills, how we integrate skills in scaling up machine learning and using parallel processing to do that. But there's also a recognition here that scaling comes with a cost. And for all of us, we have a responsibility as a data community to look at the implications of processing large quantities of data. How do we do that in a cost-effective manner? We also look at introducing fundamental concepts of ML and AI and incorporating LLMs to improve code efficiency without losing training quality. So looking just briefly now at an evolving technology we see, what's up here on the screen is the Limpopo River Basin, a transboundary river basin covering 4 countries in Southern Africa. And this is developed, this is a third-party application. So while we have all of our in-house application development, we also have a lot of users who are developing their own applications. So this is developed by the International Water Management Institute, by their digital twin team. Digital twins use advanced analytics, machine learning, and AI to analyze data from multiple sources and to simulate complex what-if scenarios. So in this situation, working with LIMCOM, the basin agency, the digital twin team has built it on the Open Data Cube technology, integrating Digital Earth Africa data pipelines and our continental services, so our newly released water body service in this instance. And the 2 graphs you see on the screen is looking at the water availability over time for the basin. And at the bottom is an example of dam monitoring. So it's comparing the multi-agent modeled output alongside our water body service. And ultimately what this is getting at is providing what-if scenarios around dam management. But what's also been integrated here is a virtual assistant. And so the team have been looking at how, particularly for less advanced users, we can integrate a chatbot which leverages OpenAI capabilities to call external tools. So they've developed plugins to handle different data types, such as to document data for the Limpopo River Basin and API for external databases. So these are all hosted, and when a user asks a question, the chatbot determines the appropriate plugin function to call, retrieves the response, and interprets the result. So the question could be around the water availability, the dry season flows, the anticipated water available for irrigation in the upcoming season. So just briefly showing you some of the developments we're seeing, and much more to come in the future, I'm sure. But thank you all for your attention.
Thank you very much, Lisa Maria, for sharing all the capabilities of Digital Earth Africa and how AI can be leveraged to support all kinds of applications. So now I would like to welcome all our panelists on stage. So please, and audience, we need your questions. So now you have the opportunity to ask the questions you've been wanting to ask for earlier. So please be ready.
Okay, thank you very much. My question is to all the panelists, because we have so many satellites now in space, all of them moving, picking data and what have you. And I think today at the opening section, there was an issue of now we should try to see how we are deploying AI to these satellites to focus on some critical issues, whether it is wildfires, it is predicting food security, and what have you. So I would like the panel to maybe comment on that to see how that will be very useful, especially for countries in Africa that may not have all the budgets to also send in a lot of satellites to space. Thank you.
Thank you very much. Excellent question. So maybe Lisa Maria.
Thank you very much for that question, Amos. So from my perspective, interoperability is key here. So in particular, the use or the preparation of analysis-ready data sets, because what that enables our user to do is to be sensor agnostic. And that is really critical as the data volumes, the range of choice just increases exponentially. So encouraging data providers to produce, prepare, and disseminate the data in analysis-ready approved formats makes them much easier to integrate into sensor agnostic approaches.
I think you are right. There are no the satellite data is available everywhere, and the data is no longer issues. In fact, the issue is how to derive the information from this data and support the decision makers or the stakeholders. I think this is the key issues. And now the data already make bigger challenges for data volumes, how to use it. So I think AI is one of the ways to achieve these data, but it's not enough. I think particularly for the developing countries, I think AI plus capacity buildings and also the trainings together can help can solve these issues. Yeah.
Thank you very much. So we have the next question there.
Yeah, good morning. My name is Mutsumi. I work at the UNFCCC Secretariat. So Thorsten, it was interesting your presentation on multi-agent systems. One thing that countries are still doing now, when they do their risk and vulnerability analysis on climate change, the officers enter the data into the computer or even with a pen, do lots of calculations, come up with the same answer that we know that 0.5 increase or decrease in that, and a new officer comes into office next month, does the same problem again. What is the potential, or what do you think we need to do now to automate this using AI so that people don't have to prove the same? We know climate change is happening. We know it's going to affect crops negatively most of the time. How can we automate this process to actually create more robust results so that people don't have to spend 3 months doing something that can be computationally done in an hour or even less? And perhaps maybe to all the panelists, my second question, with now the tools that we have, how far now are we able to start predicting the impact of the actions that we're doing? I know that now you talked about how we monitor wildfires, how we monitor crops, cropland, irrigated land, etc. But then there's a lot of adaptation actions and solutions that are being implemented. How have we already started to incorporate that to know whether the effectiveness of these actions we are doing is it active so we can replicate? Thank you.
Thank you. So Thorsten, you go first.
Okay, thank you. I think the slide where it shows Copernicus said that Greece was the biggest fire we saw, that's quite interesting or symptomatic, but we couldn't prevent it. So it's good to know it, but we couldn't prevent it, right, from happening. So I think this is the gap. And actually in Europe is in maybe other parts. This is quite pretty advanced, but as I mentioned, well, let's say even in Europe, on a subnational level, this is not used, right? So it is quite, it's just in hindsight, we know what happened, but it's not used. And we saw this wonderful example, how it could be used like on the African continent. And I think we cannot rely on the technology, right? There's a governance issue, that's number one. But and I really believe in that. It's a governance issue primarily, then a technology issue. But on the technology side, as we have seen, we have so fast advancement from 2012, when we had the breakthrough in predictive analytics or in neural networks, and then 17, we have the transformer coming, and now we're having almost each year or in 15 and 18 months, we have a new release coming from the LLM side. And I think the technology can help us to close that gap, but I fully agree on the interoperability, on the interfaces. And I think one other important issue comes into is the sovereignty of that data. Who can control those data? We see the full tokenization of the world, and when we tokenize, and we heard in the morning in the introduction, the value attached to the tokenization of Earth. We have to ensure this is done for the benefit of humanity. So these tokens which are generated, which we use also to predict, I don't need to look at the satellite image anymore. I could predict what's happening probably at one time, which makes it actually more usable even for those who don't have the bandwidth to use satellite images on a regular basis. But if we tokenize the world in that way, it needs to be accessible for the good of humanity.
Would you want to say something? Okay, second one. Anyone want to answer first? I think you touched. Okay, yeah. Please.
Yes, thank you for your question. I'm majorly answering the second questions about the tools. I think we are getting very close to make our wildfire monitoring tools in operation, and but I think there are still some barriers, majorly involving discussion with the end user, which are mostly the firefighters. So as a researcher, we are developing this kind of tools, and we're really trying to validate very hard in all kind of regions, including Africa. So we want to make it global covered, and then we want in the next step, we really want to make sure our product can be used by the firefighter, and we're making move forward towards that direction.
Thank you. Maybe I'll just follow up on that. Not only we monitor, we support, and also you can learn from the past fire behaviors from satellite images, also meteorological data. You can do prediction where there's this fire, where it's going, and how fast it's going, so that you can actually plan and mitigate. So maybe you want to.
Yeah, I think furthermore, I think after we monitor everything, how can we adapt it to the change of human behaviors to adapt to the new situations? For example, like if we do for the everybody transportation monitoring, we found out most of in the most of world we have like water shortages happens because of too much water are consumed by the human beings. In that case, we have to adapt the behavior to reduce the water consumption. Particularly, for example, in China, when we find why the groundwater is overdraft, because your agriculture is expanding too much and education consuming a lot of water. In these cases, we have to limit the agricultural water consumption in order to preserve the groundwater and restore the ecological ecosystems. I think this is the adaptation to the new findings from the Earth observations. And back to my topic on the agro-ecosystem atlas, the same. You see, in fact, there are a lot of, in fact, the land degradation and also land productivities is not matching with the agro-ecosystem characteristics. They are two, both are not matched. So once we have a new data set of agro-ecosystems, then we can replan, redesign how agricultural practices should go on. Thank you.
A question there.
Yeah, so this is Chris Justice. Thank you all the speakers for their presentations. I agree with Professor Wu's comments about data not being the big issue now. We have data, we have AI and ML methods, we have Jupyter tools that we can use. But one thing that I think is now becoming more important is what are the accuracy of the products that we're generating? And that accuracy needs to be translated into terms that users can understand. And specifically, I have a question on the wildfire products. How did you determine the accuracy of your products in terms of validating the false positives, given that fires are so transient? Thank you.
Okay, Tim.
Yes, so to validate our Wi-Fi, we are majorly using the higher resolution data. For example, if you are having some kind of active fire, then later on in the higher resolution data, we can see the burn area. If there isn't any, then the active fire can be false positive. And if there are any like burn areas in the higher resolution data, but it didn't show as an active fire point, then it doesn't belong.
Yeah, I agree. Accuracy is very important. Actually, reliability. Sometimes lack of validation data is also a challenge. Okay, we have another question there.
Yeah. I'm just following the question of Professor Justice, and I'm Bo from Aircast, and actually it's because we have a lot of products, remote sensing products, but the gaps between the products are very huge actually sometimes, especially for the land cover and maybe agriculture products. So I mean, based on the geo framework, if we need a platform and to verify from different perspectives to show the gaps and or to let users know how the gap is and how do we use this kind of data with different applications. I think that is very important. So yeah, that's my comments and questions.
Thank you very much for your comments. Our panel, do you want to have
First,
some
I
response?
will comment on the Chris
Yeah, okay.
just comments. Okay, I think is right. With AI, with satellite data, we derive a lot of information. But those informations, does those information really support to the decision makers, really benefit to the society, really support the stakeholders? This is a questions. So I think it's a need we are rethinking or develop new ways to integrate, to working together with end users to interpret these new information derived from the satellite and the AI. So I think only AI and data is not enough. Only information is not enough either. Once we how to transfer this information to support the decision makers is really next steps we need to force on.
Thank you, Professor Wu, for your comments. Question there.
Very good afternoon. Excellent presentation. Thank you very much. My question is how to make this technology scale neutral? You know, kind of heterogeneity what you have with respect to space, the heterogeneity what with respect to the spectral resolution, and also temporal resolution, how dynamic is crop, and also the forest fire. How complex is the stress what you have unless until you have a hyperspectrum? So what are the technology we have with us, how we can look future to make the technology scale neutral? That's my question. Thank you.
Thank you. Excellent question. So the panel, anyone want to answer? So maybe I can start. I think it's really a lot of training are needed in order to achieve good result for, let's say, fire or agriculture. But on the other hand, the foundation models you all have heard about, you train many images, and that's supposed to work on fire, on cover, agriculture, biomass estimation. So it is a lot of effort ongoing right now in the community, try to deploy the foundation models. So I think that's a good direction to go. And how good are the foundation models? There's some testing going on right now to see, is it really adaptable to all kinds of applications at different scales using, doesn't matter it's optical or SAR, that has to be same, but it's the right direction. Any comments from the panel? No? Okay. So I think we have other questions there. Oh, yeah, we have comments from the audience. So please.
Okay.
Share the microphone first, then comments.
Okay. Karel Garwaatman for.
Here's the next question, right? But we wanted some comments. Oh, okay. Go ahead with your question. Then we come back to this.
Karel Garwaatman for all. I will have a little philosophical and provocative question, and it is not against AI because I'm also dealing with AI. But the amount of the data is exponentially growing. Cannot be on the end limited by energy. Now Microsoft is preparing nuclear power station. Amazon is preparing nuclear power station. Will we be able in the future proceed all this data due to not have enough energy?
A good question. Thank you. So any of the panel members want to answer? Yeah.
Yes, I think in China is this approach that the data center in the West, right, and the application is in the East because all the cooling, etc., is in that region and the usage is there. So it's a big issue. It's also a sustainability issue. But I think it's currently a betting whether more data, more compute will bring us to this so-called AGI, or it's better models, better architecture. So I think now they're betting on the more compute. I'm still optimistic that this can be made renewable, right? I think it's a stage we're going through. It's like I think the neural cortex in our brain was also not invented by through evolution at the outset, but it needed all the years, the millions of years until it was developed. So maybe we have to go through that mass data, big data approach. So that would be my response to that.
Yeah, and just to add, so part of the consideration is also how data are accessed and data is shared. So it's another reason against replicating large data archives. So just to come back to my point on interoperability again.
Okay. All right. Our next question.
Okay, thank you very much. I'm Haris Kondoes. I'm coming from the National Observatory of Athens from Greece, actually. The big fires, okay, cares this also in Greece. Okay, I do agree that maybe that fires would not be all of them avoided, but they could be predicted, and we had predicted the fires. But okay, I mean, to avoid the fire is something that has to do with many other, organizational aspects that it's not for this audience today. I'm coming from the artificial intelligence domain, actually, and as in my group, we're always exciting seeing that AI is progressing so fast. And now, of course, we are in the era of the big data. We are dealing with lots of analysis-ready data, big data spaces, and of course now the new era of LLMs, etc., etc. My question always, and at the same time, my anxiety, because I'm becoming anxious each time that we are introducing some new AI technology to deal with all these big data. Are we moving too fast compared to the capability of users to adapt in what we are providing them? In other words, do we have even some smaller but good practices to provide them on their daily work so as to be convincing that what we're doing is coming to be the future and the well-being for societies? Thank you.
Okay, thank you for the question. So anyone want to answer? Touching, try.
It's kind of a natural question. I think the fast pace of AI is already translated in what we would call a risk-based approach we see all over the world. So I think society, business, governments are very much aware of what you are addressing. I think for the first time where new technology is introduced, we have a risk-based approach. So when telecom was introduced in the past century, there was not no one was afraid really of that, but there was a huge transition. When the internet came up, I think there was also more enthusiasm than we're having a risk-based approach. Actually, we had this like a innovation revolution. Software development was born, ICT was born, etc. But now with the rise of the AI, we have a risk-based approach. And first, we had all these utopian or dystopian scenarios. The question is, reversely, is a risk-based approach, and you have a regulatory approach. We see the executive order in the United States, the AI Act, or China is also coming up with a law probably next year and has already regulations on frontier AI. Is a risk-based approach sufficient actually to deal with ubiquitous, highly capable AI in the future? A risk means I don't trust human agency. Risk means I'm suspicious of human agency. And I think we need maybe also a positive ethic to say, and that's a moral approach. Morality puts trust back into human agency in a sense that businesses, mostly businesses, need to show that their AI is safe as opposed to regulators need to show their unsafety. So I think that's the shift. That sounds very utopian as well. But I think these both utopia, a risk-based approach, ensuring the safety of AI, picking up or enabling society to use that or to enable that to use it for the benefit of society, as opposed to using it for good in a way, and here in a way in a new kind of ethic. Where basically, I think, how can I say, where the word profit, the original meaning of profit means to solve problems or to progress, as opposed to make money. It's a secondary. So if we can move in that direction, that we have to solve real world problems with that, maybe then we come closer to picking up society and to using that technology.
No. Okay, I see one more hand up there, here in the middle.
Hi, Marie-Françoise Waudreau from the Open Geospatial Consortium, and I'm also involved in the Geodata Working Group. So to address the point identified by Karel on the cost, and you also mentioned the cost and the which is linked to the scalability of the issues we want to address. From the data, in the past, we were working very much on the data provider's point of view, so providing data. Here, to reduce a little bit the amount of data, we work on the concept of standardizing the analysis-ready data, prepare more data that could be highly reusable after. Then the word has switched from a user perspective. And here we have the essential variables in Geo that identify which are the variables which are the most interesting and on which we can focus to prepare all the decisions. From the technology point of view for AI, is there a stage like that where we can prepare data maybe to be more reusable by AI, or may either prepare the data or prepare some type of analysis-ready data products that could be ready for AI in order to optimize the cost and processing at larger scale or to be more efficient? I don't know if I'm clear, you know, so we have seen that from the data providers, we can reduce a little bit the scope going through this stage of analysis-ready data. From the user perspective, we can reduce the scope, identifying which are the essential variables. Can we reduce the complexity to make the global architecture and system more efficient for AI, identifying a stage like that in the middle, you know? Yeah.
Okay, thank you for your comments. And are there any reflections from the? No, I would like the panel. So I think you have a really good comments, and that's important aspects we must look into and consider. Yeah, thank you. You want to say something?
Yeah, I think you are the best person to answer this question, but I think you are right. But from the data provider side and also from user side can be should working together to make it closely to that. For example, currently there are a lot of satellite. There are some satellite that we provide hyperspectral data. But in fact, in those data, a lot of data is too much. And so, but if we can select a few bonds, which is useful for the users, and reduce the duplication from the data, will be helpful. But we don't like Sentinel-2. They are selected 20 bonds. Some of the bonds are really good for the agriculture. Some are good for the oceanography. I think that's the way. I think from data provider side, to dedicate to some particularly data which are really needed by the users, I think.
Thank you for the comments. I see there's questions there. Would you like to comment more? Let's move on to a new question. Yeah.
Okay, so yeah, thank you. So I don't have any specific questions. I just want to make some comments and to share you what we have done so far in terms of Earth Intelligence for All. So we're from a Chinese aerospace company, and actually what we do is to build AI satellites. So because we want to deploy AI in space as what Mr. Amos have mentioned. So because we believe that it's not just to share the data, we also want to share the computing resources in order to train like the AI model. And in the future, maybe we can also share the AI model for different applications for the benefit of the society. So actually, we have used our AI satellite as a free, let's say ride-share platform, or like a free computing platform for global organizations. So like we invite the global participants to join this program to like use or to train or to test their AI models on our AI satellites. And in the future, we want to build this space AI ecosystem that everyone can use this shared computing resources and to deploy the AI algorithm together and to share the use of either the data or the model. So yeah, so this is just something that I want to share to you all, and also we welcome you and also all the participants here to join this program. And our booth is actually here on site. And yes, so that's all. That's my comments. Thank you.
Thank you very much for sharing. So please give us your contacts, and we will reach out to you.
Yeah, sure.
Okay, Evangelos, you have the microphone.
Okay, thank you. So first of all, thank you very much for your contributions and also for the mobilization of the community to bring up in the agenda in geo of artificial intelligence. I have a non-technical question. these days we are going to be discussing about the new geo work program. And one of the mandates that we are having is to think how artificial intelligence can become an inherent aspect of our work program. So which transformational aspects would you foresee or expect from geo work program to promote artificial intelligence, and what would be that you would need from the geo program to promote your work in this domain?
Thank you. Excellent question. So the panelists, you want to have some reflections?
But I first refer to the young lady's comments. I think although today we have a free lunch, but in the long run, there's no free lunch. I think in the end, the users have to bear the cost for that. We can, when we are developing methodology, we can share the data, we can share the computing capacities. But in the end, user has to bear the cost. There's no free lunch in the end.
Okay, thank you for your comments. So now we have a comment on Austin's.
I think that's, if I can respond, the question of cost is a big issue, because if you have open source or open weight models, which cost millions to train, the business model, I think, is really complicated. I fully agree to that, but it creates a lot of pressure for those if this is open. But
yeah,
from my side, for the work program, of course, I would say have a task force of how agentic or autonomous multi-agentic AI could actually close the usage gap. That's what I would. What is the use case? In which stage of the process could be maybe this be thought through? What are who are the stakeholders, and how to ensure this is for the end user, for the benefit of SDG and beyond, what can be tackled there? That's what would be my suggestion.
Yeah. So, Lisa Maria.
And maybe just to build on that, I think one key role that can be played by the geo communities in providing best practice guidelines.
Thank you. So you want?
I would like to also comment on the comments from Thorsten, that I think for this kind of program, we need to bring more end user and stakeholder to to get involved in our program. For example, to promote our wildfire detection tools.
Yeah. So thank you for the reflection. Good questions from evangelists that bring us to our questionnaire again, interaction with the audience, input from you, and also what you see as AI for EU priorities. So now we start with our Metimeter again. So scan the QR code. Right. So the first question is, how can AI support your activity and your work program? It's, yeah, you can put in a free text response. All right, let's see. Okay, writing codes, identifying priority health facility data to validate prediction, accelerate the development of large-scale product, tools for analysis process and dissemination, speeds up the work, better detections and better predictions, better decisions, classifying the cases where I can't really see. Efficiency, very helpful. fast response for decision making. Yeah, so there are definitely a lot of areas. Okay, then we even have work translator enable unbound communicating among all participants, improve efficiency. So I see efficiency, effectiveness, increase the involvement. So looks like everyone is looking at efficiency, accuracy, and scalability. So that those seems to be like common elements. Nice. Okay, our next question is, what are the top 3 priorities for AI for EO subgroup if we were going to create such a subgroup within GEO work programs? So what do you see as the top priorities? Give 3. Yeah, your inputs are important in shaping, you know, the future of the work or the working group. Novel architecture, labeling agents, inclusive AI, data source. Let's see, platform, I guess it's access to data processing platforms, like access to labels. I can see quite a few labels, training data, data scalability, data management, data utilization. Yeah, there are quite many. User friendliness. Sometimes AI models, maybe you need some skills. So if we can have tools that are easy to use. Best practices, sharing best practices are important. Link to EO AI communities. Yeah, there are quite many inputs. We will take your inputs into consideration to set priorities for this working group. Yes, great input. Thank you, everyone. So now we are going to our next question. What was the major takeaway from this session for you? So yeah, your feedbacks are welcome. The set of art, advancing, moving further from what user can manage. AI cannot solve all issues. Learning the method of AI for fire detection, idea, the impact of AI in geo, the importance of decision of collaboration, design of collaboration of public and private sector, learning the method of governance needed. We need stronger integration with the ESG plus I. Every lunch is not free, that's good. Community engagement, effectiveness of AI solutions, sustainable water use in agriculture. AI is here to stay and we need remove fear and implement. How much AI can be incorporated in EO, need to coordinate and optimize fragmented efforts. We have the technology, but we have some governance issues, the benefits of AI and the benefits in future, need for interoperability, document quality of the processing and outcomes, ML training challenges, optimize costs, reliability. So yeah, so many takeaways. So thank you very much for your input, and we really appreciate our, let's see, can we move to our last slide? Big thanks to all the panelists for their presentations and input. And also special thanks to Wenbo and Hannah from the GR Secretariat for their support to this session. So thank you very much. And thanks to all participants for participating in this session. Thank you very much. Don't forget to contact us to join the AI for EO subgroup. Thank you.
So I have a few housekeeping announcement. So I hear that the housekeeping at the auditorium was too fast, so people didn't get to take all the information. So for those of you who haven't collected the badges, so all the badges and the bags have been moved here, just outside, just in the exhibition hall in the back. So you can collect your badges there. And if you still don't have a Wi-Fi code, they have a printed sheet for you. So also go there and collect. And the live demos, so we do have a lot of live demos arranged. In morning session, morning coffee break, and also during lunchtime and afternoon coffee break. So coffee break lasts 45 minutes. So the live demo will start 15 minutes after that. So we understand people also want to, grab something and chat it a little bit, but go to the live demo stations. Our colleagues want you be there. So there are 4 corners and 1 on the side. So in the exhibition hall, go and find those screens. And there's another station in the middle, get your vitamin C. This is Jill's communication station. There will also be live demos. And basically there's a board of a schedule. You can see how these live demos are scheduled for the from today and onwards until Thursday. Yeah, that's about it. And for the live demo at the noon time, it starts at 1, I believe, 30 minutes after lunch. So you can take some food and enjoy the exchange with colleagues. Thank you so much.